Hello guys, today I would like to discuss the Euler's identity e to the I pi plus 1 is equal to 0, and I would like to show you how to prove this Euler's identity, which is dubbed the most beautiful equation in all of mathematics. Even the late great physicist Richard Feynman in one of his lectures called it our jewel and the most remarkable formula in mathematics. Okay, to begin the proof, we start by using the power series expansion, which says power series expansion for any complex number z, we have that e to the power of z is equals to 1 plus z over 1 factorial plus z squared over 2 factorial and so on. Yeah, this is the power series expansion of e to the power of x for any complex number z. Okay, now that we have this, we take as well some basic fact about the power of I, where we have I, which is power of 0 is 1, I to the power of 1 is negative 1, is 1, I square is negative 1, I cube is negative I to the power of 4 is plus 1, to the power of 5, and so on. Yeah, these are some basic facts about the power of I, and we're going to use this and put them into this equation when we take z is equals to ix. Okay, when such action is carried out, we have e to ix is equals to 1 and so on. This is just putting, since I said let's take z equals to ix, it's just putting this into the expression we had before. Then when we have this, we then expand it further to have 1 plus ix. Now I square is just negative 1 as we had before. Then we have minus negative x squared over 2 factorial minus ix cubed over 3 factorial plus x power of 4 over 4 factorial plus ix5 over 5 factorial minus x power of 6 over 6 factorial minus and so on. Now the next thing to do, of course is to take out the factors that contains I, bring them out into one side, and those that are just left without I, that's we have 1 minus x squared plus s4, bring them outside. Then when we take such action, we have 1 minus x squared over 2 factorial plus x power of 4 over 4 factorial minus x power of 6 over 6 factorial and so on. You put that in a bracket. Now because we're taking the values that contain I, then we bring out the I out plus I, then we have x minus x cubed over 3 factorial plus x power of 5 over 5 factorial plus x power of 7 over 7 factorial and so on. Now from this we can get that e to the power of ix is cos x plus I sine x, where cos x and sine of x, where this is just the Maclaurin series expansion for the trigonometric function cosine and sine of x. So now this, what we're able to show here is what we call the Euler's formula. Yeah, this is created to Euler, and it is an important formula in complex analysis. Now, but we're not done with this, because what we want to show is the Euler's identity. The Euler's identity e to the power of I plus 1 is equal to 0. Now, for us to do this, we'll simply say let x equals to pi. Now when x is equal to pi, it's being substituted into this expression here. Then we have e to the I pi is simply cosine of pi plus I sine of pi. Now pi is in radian, pi in degree is 180 degree. in degree, and you can convert this to radian using a particular formula. Now when we have this, we have the cosine of pi is -1, and this is just 0. So in that case, we have e to the power of I pi is equal to -1. Now when we bring it here, we have e to the I pi plus 1 is equal to 0. Of course, this is the famous Euler's identity. Okay, I've been able to show you how to prove this, and I hope you really enjoyed the video. Please, if you want more videos, please don't forget to subscribe and like, and I do look forward to hearing from you in the comments. Thank you.